Hello everyone. Today we're going to cover your first lab for your computer architecture course. In this first lab, we're going to take a look at VerySimpleCPU and the tools we will be using in this course. So, the first part of this lab is the background. Here we will cover the basics of VerySimpleCPU and our tool, the ISS, which is a simulation model. Then we will talk about the instruction set of VerySimpleCPU, and then we will see the different implementations of the model on different operating systems. So first of all, we will be using VerySimpleCPU throughout the course. And in order to write programs for VerySimpleCPU, we will have to test them. For testing these programs, we will use the ISS. This is a simulation program which I am going to introduce you to now. In this program, you input an assembly file, and the program simulates VerySimpleCPU architecture and gives you the output. Before we start actually working with this though, let's familiarize ourselves with the instruction set of VerySimpleCPU. So included in the lab files, you will see a file called instruction set readme. I will be going through this file and introducing you to the instruction set of VerySimpleCPU. Now, the first thing we should familiarize ourselves with are the instruction words of VerySimpleCPU. Now, as you'll see from this figure, each word in the VerySimpleCPU is 32 bits, starting from bit 0 to bit 31. And the different ranges in these words have different meanings. And these are the opcode, the I bit, the A value, and the B value. So, going in order, the opcode tells the CPU what operation to perform. The I bit is something we call the immediate bit, and I will go into more detail about this later through examples. And then we have the A and the B values, which are going to be either values or addresses, which will be used in operations. So, let's start looking at our individual instructions and see what each of them do. The first instruction is the add instruction. This is a very straightforward instruction where the value in A is added to the value in B, and it is written to A. Now, these notations here are actually pretty important, so let's take a closer look. So you'll see here, instead of using a simple notation as A equals A plus B, we have this star notation here. So this star notation means that we are referring to the value inside an address. So you might be familiar with this notation if you have taken courses involving C++ or C. It is actually the pointer notation. So this star A means the value of A. If it was just A, it would mean the address A. So what this line here is saying is the value of A is equal to the value of A plus the value of B. So with this means that this instruction takes the value of A and the value of B and writes it back to the value of A. And as we've discussed, these values come from these words. So from bit 27 to bit 14 is the address A. From bit 13 to bit 0 is the address B. And what the CPU does is it looks at this address, goes into that address and uses that value. So let's take a look at an example. So let's say at our 0th address we have this instruction, add 5, 6. And at address 5 I have 2, and at address 6 I have a 7. So after this instruction is executed, let's see what these values look like. So when this instruction is executed, the first thing it does is look at the value inside 5. So the value inside 5 is 2. And then look at the value inside 6, which is 7. So let's go back to our instruction set. What it's going to do is take these two values and write it back inside A. So it's going to do 2 plus 7, which is 9, and it's going to write it back to 5. So instead of 2, we're going to have a 9 here. All right. I think that covers the first instruction, our add instruction. Let's go on to our second instruction, which is add I. Now, this add I is a variation of the add instruction, but the difference is here, if you remember, I talked about the I bit. So this time, so previously in the add instruction, the I bit was 0. But now in add I, the I bit will be 1. You can think of this as the immediate mode disabled and enabled. It was disabled in add instruction, and now in add I it is enabled. So let's take a look at what that's going to do here. So let's see this notation here again. So again, the value of A will be equal to the value of A plus B. Now be careful here. We do not have a star in front of B this time. So it is not the value of B, but it is just B. So what this means is that instead of interpreting B as an address, it's going to be treated as a value. So I think it's easier to show this with an example. So let's have the same example, but instead of add, we're going to have add I. So add I 5 and 6. So this time, let's go back to our instruction. The value of A is going to be value of A plus B. So value of A is, let's go back to our default state, which was 2. So the value of A is 2. And we're not going to check the value of B, but we're just going to use this value. So it's going to be 2 plus 6, which is 8. So the value of A is going to be 8. So this is the main difference between having the immediate mode turned off versus on. Next up, we have the NAND, bitwise NAND instruction. So the operation-wise, this is very similar to the add instruction, but instead of doing an addition, we're going to do a NAND operation. So this is how we show a NAND operation. The value of A is and the value of B, negated will be the value of A. So how you do this would be something like this. Let's say again 5 and 6. Well, something to be careful about here is this is a bitwise operation, so it would be easier to show this in a bitwise manner. So instead of showing 2 here, I'm going to write it in this notation. So each of our values in VerySimpleCPU is 32 bits, so this is going to be something like this. So I'm just saying this value is 32 bits wide, and then in order to write 2, I'm going to have a bunch of zeros here, which I'm not going to write all of them, and then I'm going to have a 0, 1, 0 at the end. And then as for 7, again, 32 bits, bunch of zeros. And then for 7, it's going to be 1, 1, 1. So that is 4 plus 2 plus 1, which is equal to 7. Alright, so this time we're going to do a NAND. So when we do a bitwise NAND, we're going to look at each of these bits and do a NAND. So it will be something like this. So let me just copy this for sake of just showing this. So 0 and 1 would be 0, but since it's NAND, it's going to be opposite of that, so it's going to be 1. 1 and 1 would be 1. Negate that, it's going to be 0. And then 0 and 1 would be 0. Negate that, it's going to be 1. And then these are all going to be 0 and 0, which would be 1, but instead they're going to be 1. So at the end of this instruction, of course this is not 6, this is 5. The value inside 5 will be this. On to our next instruction, which is NAND I. Again, this is very similar to the relationship between add and add I. Instead of treating the B as an address, we're going to treat it as a value and use it immediately. So next instruction is SRL, which is a shift right or left. Now there's a condition here, and let's see what this is about. So shift right if the shift amount, the value of B, is less than 32, otherwise shift left. And a good way to remember this is SRL. So the default operation is to shift right, and the default condition is B, with the value of B being less than 32. Now the value 32 here is significant because the width of the value stored in VerySimpleCPU can be only 32. So shifting more than 32 is actually meaningless. That is why we use the value 32. And then let's look at our this notation again. So here you might have an unfamiliar notation here. So this bit here and this bit here. So basically what this is actually very simple. Let me just copy this and show you this in a format that you might be more familiar with. So what this says is actually this. If b, the value of b is less than 32, the value of a should be equal to a, the value of a shifted by the value of b, else the value of a should be equal to the value of a shifted by b minus 32. And this is a simplified notation, a one-line if, and it's actually called a trinary operator, I believe. It means the same thing as these 4 lines. So we can take a look at this as in an example. Let me just open a new file here. And let's say we have SRL, again, 5 and 6. And in 5, I have, let's say, 8. And in 6, I have 2. Now, again, it's easier to show this in binary notation. So let's switch to that again. So I'm just gonna copy it from here to make it a bit easier. So let me just put this here. So this is going to be 8 and this is going to be 2. So since this is 8, I'm actually going to do this. Whoops, something like this. So this is 8. And then 2 is simply going to be like this. Alright, so now let's take a look. So the first thing we should check is whether the value b is less than 32. So if you remember, if the value is less than 32, we're going to shift right. So since the value is less than 32, let's shift right. And let me add a 0 here just to make it a bit simpler. And let's see. So our job is pretty simple here, since we have all zeros here except just one. So let's just track where that 1 goes. So we're going to shift this by 2 to the right. So that means this one is going to go here. Sorry, it's going to go here. And then one more is going to go here. So our result is going to be like this, which is, again, 2. And then let's do another example. Let's separate this. All right, let's say, let's keep this 8, and let's say this is 34. So 34 is going to be something like this, I believe, right? 32 plus 2 is 34. And let's expand this as well. There we go. All right, and we're going to have to expand this as well. There we go. So let's set this to 0. In fact, let's just put 8 here. Okay, so now we have 8 and we have 34. And as we know, 34 is greater than 32. So what are we going to do? So if the value is greater than 32, what we're going to do is we're going to shift left by that value minus 32. So in this case, 34 minus 32 is 2. So that means we're going to shift left by 2. So instead of 8, we're going to get what? It's going to come here, and then it's going to come here. It's going to be 0. So we're going to get this value, which is 32. So on to our next example. Again, our next instruction is going to be SRL-I. So this is going to be the SRL with the immediate bit enabled. So again, instead of treating the B as an address, we're going to treat it as a value. Meaning that, if you were to go back to this example, if this was SRL-I, we would have to shift by 6. So we would have to shift to the right by 6 instead of shifting by 2. But since we've done several examples like this, I'm going to skip it. Our next example is less than. So this is a logic operator where the value of A is compared to B, and if the value of A is less than the value of B, the value of A will be set to 1, otherwise it will be set to 0. So here, if you look at our notation again, the value of A is equal to the value of A is less than the value of B. Let's again take a look at an example. This should be pretty simple. So let's say less than 5, 6, and in 5 I have 5, let's say 4, and in 6 I have 8. So in this case, what's going to happen is we're going to compare the value 4 to the value 8. And since the value 4 is less than 8, we're going to set the value of A, which is 5, to 1, which stands for correct. And if we were to take a look at a different example, I'll say let's have the same instruction, but let's change our memory. Say 5 has 12 in it and 6 has 8 in it. So in this case, sorry, that's supposed to be 6. So in this case, 5 is not less than 8, so it's false. It's going to be 0. Next up, we have LTI, and LTI again is the less than instruction with the immediate mode enabled. So instead of treating B as an address, we're going to treat it as a value. Next up, we have a copy operator. So this operator is actually very simple. What we do is copy the value of B into the value of A. So a very simple example would be CP56, and in 5 let's have 1, and in 6 let's have 5, let's have 8. The result is going to be 5 is going to become 8, and 6 is not going to change. It is also going to be 8. Next up, we have the CPI, the copy immediate instruction, where this time, if I say CPI 56, instead of looking at the value inside 6, I'm just going to use the value 6. So in this case, 6, the address 6 will remain the same, but the value of 5 will become 6. Now we're going to talk about the copy indirect operation. Now this is a slightly more complicated operation. Here you'll see a new notation. This notation is star star b. So if we were to base this on our previous notation, this would be the value of b. So what we're going to do is we're going to do 2 lookup operations to find this value. So let's actually just do this with an example. I think it'll be a bit easier to understand. So CPI, say CPI, let's say again 5 and 6, and inside 5 let's have let's say 9, and then inside 6 let's have 10, and then inside 10 let's have 3. Alright, so what's going to happen in this case? So in this case, again, let's look at our notation here. It's star star copy star star. Let's actually look at this. The value of A is equal to the value of A. So let's deal with this part first. So we're familiar with that already. So we're going to assign something to the value of A. So we're going to assign something to here. Whatever value we find, we're going to write it here. And then next, we have star star B. So when we see a star, what we do is we follow the link, right? So if you see a 6 here, we're going to follow the link and we're going to get to 10. And then usually we stop here. We just use the value 10. But instead, we're going to keep following this value now. We're going to go and see what star 10 means. And star 10, in this case, the value of 10 means 3. So we're going to use this value 3. And if we go back to the instruction here, what we're supposed to do is we're supposed to just copy this value into the value of A. So at the end, what we're going to get is just this. 6 and 10 are not going to change, but the value of 5 is now going to be equal to 3. Alright, so on to our next instruction now. So our next instruction is CPI-I. So in the previous instructions, enabling the indirect bit actually just changed a single thing. We treated B as a value instead of an address. But in this case, this is not exactly what it does. So this just completely changes the behavior of this instruction. And what it does is it will copy, we are supposed to copy the value of B into the value of A. So we're kind of doing the opposite of what we did in the previous instruction. So let's take a look at our notation here. So we're doing star star A. So the value of A is equal to the value of B. So let's just compare these two now. So in the previous instruction, we had the 2-star notation on the right-hand side of the equation, right? So this is also called indirection. So we have the indirection on the assigned, so to the assigned value side. This time we have the indirection onto where we're assigning the value to. So this is the difference between these two instructions. And I think this will become more clear with an example. So let's copy this and see how this operates now. So this time we don't have star star B, but we have star star A. So we're going to have to slightly alter this part here. So we have 5, which is 9, and then 6, which is 10. So this is no longer relevant, so I can delete this. But instead, what's relevant is the address 9 this time. And let's say the value inside 9 is 7. So what this instruction will do is the following. So we'll say 9 here, and let's actually put this down below. It'll make a bit more sense. So let's follow our links again. Let's just start with star B again. So that part's a little easier. So star B, the value of B is going to be 10. So this time what this means is that we're going to assign the value inside here to wherever location we decide. And this location is going to be determined by A here. So star star A. Let's start by following the links. So follow the link here, 9. And we still have one more star, so let's follow the link one more time. We have 7. But in this case, the value 7 is not very important, but what's important is the location 9. So what's going to happen this time is we're going to take the value 10 and we're going to copy it into the 9th address. So sorry, let me fix this. This is going to remain 9, this is going to remain 10, and this is also going to be 10. Alright, so on to our next instruction. Our next instruction is called BZJ, and it stands for branch on 0. So what this instruction does is we will check the value of B and see if it's equal to 0. And if this value is equal to 0, we're going to jump to the value of A. So the term jump might sound unfamiliar to you. So let's actually see this with an example, and that might make things a bit more clear. So let's have our instruction be the same as usual, BZJ 5 and 6. And inside 5 we will have 2, and inside 6 we will have 0. And for the sake of demonstration, I'm going to put additional instructions here. So in address 1, let's say we have CPI for 1, and let's have let's see, add I for 1, and let's start our program with 4 assigned to 8. Alright, now let's see what will happen when we execute this program. So we're starting with the address 0, and what would usually happen is after executing this instruction and altering the memory, we would go on to execute the next instruction, which is the instruction in address 1. However, BZJ and the instruction BZJI are an exception to this. So as we said, BZJ stands for branch on 0 jump. So what we're going to do here, let's go back to our instruction set. What we're going to do here is we're going to check the value of B. So the value of B would be 6. Rather, the address B would be 6, and then the value of B would be 0. And then, if this value is equal to 0, we're going to set our PC, which stands for program counter, to A. So in this case, we're going to set our program counter to value of A, which is 2. And basically the program counter tracks whichever address you're currently on. So currently our PC is at 0, and since B is equal to 0, we're going to set our program counter to the value of A, which is 2. So instead of going on to the next instruction at address 1, we're going to skip to address 2. So the result will be something like this. 4, 5, 6. So the values here will not be edited, changed in any way. So yeah, BZJ does not actually change any values in the memory. What it does is alter where this program goes. So as we said, we're going to skip this instruction and go on to do the instruction at address 2. So which is add I for 1. So this is going to alter the 4th address. We're going to add 1 to 8, which is going to become 9. And then let's see the example where the value of B is not equal to 0. So I'm just going to copy this and paste this same situation here, but instead I'm going to set the value of 6 to something else. Let's say 5. So let's execute the same program again. This time I'm going to check the value of 6, which is 5. But this time it's not equal to 0, which means I'm just going to increment the program counter, meaning that I will start executing the next instruction now. So what's going to happen is I'm going to copy 1 into 4, so this will become 1, and I will go into the next instruction where I will add 1 into 4, so this is going to be 2. Alright, so on to our next instruction. This is again a different version of the BZJ instruction, BZJI. This time we do not have a conditional. So in the previous one we said we had a conditional, and if the conditional was satisfied we would jump. This time we're just going to jump. So let's see. What this says is we're going to set the program counter to the value of A plus B. So a simple example would be like this. BZJI, again, let's have the same example, 5 and 6. And let's have the value of 5 be 1, and let's have the value of 6, which is actually irrelevant. Let's set this to 0. And then in this case, I'm going to have some instructions here. But what's going to happen is when I get to here, what I'm actually saying is read the value of A, which is 1, and then add B into this. So 1 plus 6 is 7, and jump to this value, to this address. So I'm going to jump here. And of course there's going to be an instruction here. So instead of going 0, 1, 2, 3, 4, we will end 0 to 7. Right, so on to our last two instructions. It is the multiplication instruction. So this is actually a fairly simple instruction where we multiply the value of A and the value of B and assign it to the value of A. This is very similar to our previous examples like add, NAND, and SRL. So I'm not actually going to do an example. And similarly, we have the immediate version of this, where I'm going to multiply the value of A with B and I'm going to assign this to the value of A. Alright, so that is it for our instruction set. Up next, we'll see how to use our simulation program. So a side note here, so most of you are going to be on Windows, and those of you who are on Windows are going to use the program that we're going to provide with you, but those of you on Mac or Linux can go to this site here, which has an execution of the the implementation of the simulator on a web page. Look at here, and you can use this site for your simulation. For the sake of this video, I'm going to do this on Windows, so just be aware. Alright, so I'm actually going to show you how to use the program through your lab work. So let's actually do some of these steps, and I'm not going to go into too much detail, but I already have most of these things set up. So you're going to create some folders and put some files in there. I have most of those set up, so I'm just going to go there. So what you're going to do is you're going to open these two files here. These are the examples that we've already given you. We just want you to compare them and analyze them and try to understand what's going on. So let's actually open them and see what they're about. So Lab01 Part 1 minimum .asm and Lab1 Part 1 minimum low.c. Minimum.asm and minimum low.c. So we want you to open them and compare these two. So these are actually the same program, one written in C, one written in our VerySimpleCPU assembly. And one nice trick for comparing these two is the following. So if you're using Notepad++, you can drag and drop one of these onto the screen and then say move the other view. And if you do that, you're going to get something like this. Let's zoom in with this as well. So as you can see, this is a great way to compare these two files. You can compare what's going on and see what's going on. So basically, the reason we gave you these two files is that when writing programs in assembly, it's very hard to do it directly. So what we usually do is we write them in a higher level program, in this case C, and then we convert it to assembly. So after you open those of these files and compared them, let's go on to the next part. In this part, we're going to open a command prompt and then execute our simulation model. So I'm actually going to show you a very easy way to do this. So what you want to do is go to your workspace and then into VerySimpleCPU, where you have your VerySimpleCPU.exe. And what you want to do is press this here, this address bar, delete this, and type cmd. And when you press enter, this will open a command prompt in this directory. So after you've opened this, you're going to copy your assembly program into here. So you don't actually have to copy it, but it makes things simpler. So I'm going to open another window here. Here I have my files. So what I'm going to do is I'm going to copy this assembly file into here to make things simpler. And I'm going to type the command in here. So VerySimpleCPU.exe, your input file, R, and then a greater icon, and then log. So let's type this and see what happens. So very simple, and in the command prompt what you can do is type the first few letters of your program and then press tab. Windows will automatically autocomplete the file for you, and then space. Then we're going to write the name of the assembly program, so Lab01. Let's press tab. There we go, we have that as well. And then next up, you're going to write R, which stands for run, R, and then this symbol, and then log. And you can actually add log.txt to make it actually a bit easier on you. And once you run the program will stop, and you will type exit and press enter. Now our simulation has been completed and the log is inside log.txt. So once you're done, you can look at the log file, which is going to be in the same directory, log.txt. And this file will actually show you what's happening in each instruction. So let's put these actually side by side. Here we go. So this says that in instruction 0, this is my instruction, this is my program counter. I had this, and after executing it, I had this. Similarly, for instruction 1, I have this part, instruction 2, and so on and so forth. What we want you to do is inspect this part and try to understand what this program does. Once you do this, you will have a look at a text file called memout.d.txt. So let's see this memout.d.txt. So this file here is actually the output memory of the program. So let me put these side by side again. Here we go. So this is so this line here is this instruction converted into decimal. And here you will see the output memory, and you might notice a few differences. So 6 didn't change, 101 didn't change, 102 didn't change, but 200 changed. So here, this is actually the effect of the program. And we want you to confirm that the output, which is at the address 200, is the smallest among the value 101 and the value of 102. Next up, we want you to rewrite the C codes and the assembly codes that we gave you. And we want you to, instead of finding the minimum, we want you to find the maximum this time. So in the previous one, you found the minimum value between two values. Now you're going to find the maximum value. And once you rewrite these three files, the high C, the low C, and the assembly file, you're going to simulate this assembly file and confirm the results through the memout.d file. So I actually have the answers, so let me do this procedure. So let's again repeat this. I have my VerySimpleCPU here, and then I have my completed assignment here. So what I'm going to do is I'm going to copy this here into this directory, and then I'm going to execute this instruction again. And what I'm actually doing here is I'm pressing the up arrow key to copy the last instruction that I've executed. But the only difference is I'm going to change this file name here. I'm going to execute this. The program is going to stop after a while, and I'm going to write exit. And I'm going to check the memout.d. So let me actually open the assignment as well, the empty template assignments. Well, actually, we can just look through here. So we had our values in 101 and 102. So in this case, our values are 220 and 37. And I'm supposed to find the maximum among these and write it to the address in 200. In this case, the maximum value is 220. So once you've confirmed this, you're good to go. Yeah, this assignment is done. And if you have problems with this, what you can do is check the log file, which I'm not going to show you right now, to debug your program. So with this, the first part of the assignment is done. So the second part, we're going to have a different program. You're going to work with the programs that you wrote in the previous part, the maximum high, maximum low, and maximum assembly files, and you're going to edit them such that they're comparing 3 numbers instead of 2 numbers. So this time I'm going to compare the values in addresses 101, 102, and 103, and I'm going to find the maximum and write it to the address 200. And I'm going to perform the same procedure and check the memory memout file to confirm that I am done. Let's do this real quickly again. So I have mine here. So part 2, I'm going to copy this here. And let's execute this. So lab01, not part 1, but part 2. And there we go. I'm going to type exit. And now, if I go back to Notepad++, my memout should be updated. And in this case, my values were 130, 150, and 110. And the maximum among these is 150, so that is going to be written in address 200. Once you've confirmed this, you're done with your lab, and you can send your files. There are rules regarding your submission. So you will be submitting these files to your LMS. Don't zip them. Don't change their names. They should be exactly named like these. Send them through LMS and you will be done. Thank you for listening. This is the end of our first lab, and see you next time.